Now, before we get quantitative in part B, we first consider the basics on why micelles and bilayers form, and this is the physics of self-assembly. So the question that we would like to address is, how can it be that a bunch of molecules here on the left side will spontaneously form structures, ordered structures, like these lipid micelles or a lipid bilayer? Now, a good start is to look on part of the process and the energies concerned. I show here a table of experiments that show the energies involved into the process where oil molecules have been put from the water phase into an oily phase. You know from making your salad sauce that mixing oil and water doesn't work. Oil wants to stick to oil and water would like to stick to water. So the first idea would be that there is more attraction between oil molecules and more attraction between water molecules than vice versa. However, the numbers on this table actually tells this is not true. If we look on the inner energy, which is here called delta H, for this process, you see that actually energy is needed to put an oil molecule from water into an oily phase. Delta H is positive. Now, in the last lecture we learned that whether a process is going into either of the forward or the backward direction is not given just by the energy, but by the Gibbs free energy, which contains two parts. First is the change of the inner energy, delta H, and a part that concerns a change in the entropy, minus T delta S. Now, looking again into this table, you see that delta S for that process is positive, hence making that delta G is negative, and you have the separation between oil and water. Just to make clear, so how do you get actually these two separate values in an experiment? Well, what you do is you calculate the concentration of, in that case, oil molecule in water, and relate this to the equilibrium constant, which was given, as we found in the last lecture, by e to the minus delta G divided by kBt. Now, knowing that delta G is given by delta H minus T delta S, you see that delta G has a temperature dependent and a temperature independent part. Hence, the temperature dependent part of that experiment would give you a value for delta H divided by kT, whereas the entropy part would be a constant value. Now, before we go on discussing the different parts, let's consider again back the energies involved in this process, but then calculate it not in a way that typically chemists or biologists would do in kcal per mole, but in physical units. That means, for example, what is the energy involved for a single molecule, and we express the energies in units of kBt, where T is typically the room temperature. So if we translate the delta G, we find that per molecule of lipid in this process, going from water into the oil phase, there's a delta G of minus 6 kBt. So a sketch of a lipid I drew up here, where the size of the head group is in the order of 0.3 nanometers, and the length of these fatty acid side chains is between 3 and 5 nanometers, typically. Now, what we could do is, now we could consider making up a line of these kind of molecules and then calculating what is the energy per length for the process given. So if we just plug in all those numbers, what we come up with, that the energy, it's a sort of line tension, is proportional, is about minus 3000 kBt per micron. Likewise, we also could consider, if we have this molecule here, we can calculate the surface energy involved in such a process. So we assume the lipid is just a cylinder, and from that we can calculate the surface, and we end up in a surface energy of minus 2 times 10 to the power 7 kBt per square micron. Now, these numbers we will come back in what follows. So let's look back in the initial table that I've shown, and here find the delta S in this process. So again, the process is you have oil molecules dissolved in water and place them into an oily phase. And in this process, you see that the entropy is increasing. Yet this is counterintuitive. We start out with a well-mixed solution where oil and water is completely mixed, and we end up in an ordered and sorted phases of water and oil, which would mean that the entropy is decreased. However, this view is only a view if we just consider the oil as a particle. We have to look a little bit closer in how oil is dissolved in water. So in water, the hydrocarbon chains are just coiled up and surrounded by water molecules. However, the water molecules on the surface of the oil molecule are highly ordered, where all the hydrogen atoms of the water molecules are oriented towards the oily phase, whereas the oxygen molecule is pointing away. Hence, the entropy increase that we see by starting from an oil molecule in water, going to an oil molecule in oil, is due to the increase in entropy of the water, so the solvent, and not due to the entropy of the oil. This is called the hydrophobic effect, and it's due to the structuring of water around hydrocarbons. So the hydrophobic effect tells that entropy is driving the separation of oil and water. Now, in the next step, we look on an experimental observation. In this experiment that is described in this figure, the total amphiphilic concentration has been increased. Now, at very low amphiphilic concentration, to the left of the figure, you will find that all amphiphils are just dissolved in water. Now, by increasing the amphiphilic concentration, you hit a given concentration, which is called the critical micelle concentration, at which micelles will occur. And this is a nonlinear process. As soon as the micelles occur, so if you further increase the amphiphilic concentration, you only increase the concentration of the micelles, and the amphiphilic concentration that is just as a monomer in the solution stays constant. Now let's try to make up a model in order to explain the formation of micelles and the occurrence of the critical micelle concentration. The model that we make up is just a chemical model. So we say there is an equilibrium between n monomers and the micelle, which contains n monomers. Now, from what we learned last week, the ratio of the concentrations, so the Cn, divided by C monomer to the power n is given by the law of mass action and equals to the equilibrium constant. Now, this last expression we can rewrite, just giving us an equation for the total amphiphile concentration, C total, which is the sum of the amphiphiles residing in as monomer and the sum of the amphiphiles that reside in the micelles. And we come up to an equation that only contains the amount of amphiphile concentrations that we add to the solution, which is C1. Now this equation reads C1 times 1 plus n times K equilibrium times C1 to the power n minus 1. Now we define the critical micelle concentration as the concentration where the concentration of monomers at CMC is equal to n times the concentration of micelles at CMC, which in other words is just CMC half. Now we use our definition of the CMC in the law of mass action, and we obtain that the equilibrium constant K equilibrium is equal to 1 divided by 2n CMC times CMC half to the power minus n. From there we can rewrite our equation for the total amphiphile concentration, C total, as a function of C1, the dissolved amphiphile, and that reads is equal to C1 times 1 plus 2C1 divided by CMC to the power n minus 1. Now in this graph I show how the total CMC concentration, C total, depends on either the monomer concentration, C1 divided by CMC, or by the total amphiphile concentration in micelles, n times n Cn. Now in order to compare our result to the experiments, we just now flip and rotate our solution, and we see that as seen in the experiments, our very simple model can easily explain the experimental results. So the take-home message from these experiments is that the occurrence of higher order structures and self-organization needs a critical concentration of the monomers in order to occur. And this is explained by the critical micelle concentration in this particular experiment. Now you might wonder where the critical micelle concentration depends on. And this is what we're going to analyze in the following. Now we saw that there is a critical micelle concentration, and experiments have been done where two things have been changed. The first is the length of the hydrocarbon chains of the amphiphile. So in the right you see how the CMC depends on the length of the hydrocarbon chain and C of the amphiphile. The plot is a log-lin plot. That means so it's the CMC exponentially depends on the length of the side chains. Likewise, you see that for amphiphiles that have two hydrophobic side chains, which is typical for lipids of the cell membrane, the curves even drop down further because there are two lipid chains now. Now let's try to make up a model for the interpretation and the understanding of these experimental results. For that we need to remember that the occurrence of self-organization is driven by the free energy of the system. So let's first look on the inner energy, so the energy that is needed to extract a lipid from a micelle. Well, this energy is equal to the surface of one of those molecules, let's say a single lipid, times the surface tension. So we model the amphiphile, or the lipid, just as a cylinder of radius r and length nc times L, where nc is the number of hydrocarbon, the length of the hydrocarbon side chain, and L is the length of one unit. So typically L is in the order of 0.3 nanometer. Now, the surface of the cylinder is then given by 2 pi r nc times L, and that we have to multiply by the surface tension, gamma. Likewise, we concern the entropy of the lipid. So there we know that the entropy is given by minus kBe log of the concentration. Now, at the CMC, the energy, inner energy, equals the entropy, from which we obtain the equation 2 pi r nc L times gamma is equal to kBt times the log of the critical micelle concentration. We solve for this critical micelle concentration and obtain CMC is equal to e to the power minus 2 pi L gamma divided by kBt times nc times r. This is exactly what we were after. We see that the CMC scales like the exponent to the power minus nc. That is exactly what we saw in the experiments. Likewise, we see that the CMC also scales like e to the power minus r, hence depends on the radius of the head group, where the head group of lipids is larger than that of just a regular amphiphile, like a detergent. Hence this curve, the black curve, shifts to the left when we are concerned with lipids. Now, that part of the lecture explains how we can understand in terms of statistical physics, how the critical micelle concentration comes about, and we made also a predictive model how the critical micelle concentration, for example, depends on the length of the side chains. The basic take-home message of this clip here is that it needs a certain concentration in order that self-organization will occur. Now, in the following clip, we will address why lipid vesicles will exist at all, and we come to a surprising result, namely that mechanics determines the typical size of vesicles, and those actually also occur in nature.